Feel free to stop me if anything gives up, or I usually give talks to math departments. So if there's anything that's confusing, feel free to bring it up. Um, so yeah. So say you have a geometric object. Then how do you visualize that object? You can draw a picture. You can draw some if you can draw some sort of picture, which is some way to represent it in 2 dimensions. But if the object is very complicated, then the picture won't really reflect the structure of the object. You can go higher dimensional. You could say, okay, well, this isn't really a picture in 2 dimensions. Maybe this is some 3-dimensional picture of my object. And so I can rotate it, get different angles. But if the object is really complicated, then the 3-dimensional picture isn't going to give a good representation either. And ultimately, you can't take a 100-dimensional cube and squash it into 3 dimensions without some loss. But the thing is that even if you allow for embeddings into very big spaces, even if you allow for embeddings into infinite dimensional spaces, you can still construct objects that don't really fit in the space. So one example of this is random graphs. If you have a random degree 3 graph with a million vertices, you just take a million vertices and connect them at random so that you get a degree 3 graph. That's something called an expander. And expanders have geometric properties that make them impossible to embed in Rn and impossible to embed even in infinite dimensional spaces, even in Hilbert space L2. And so there are applications of this in computer science. There are algorithms where the accuracy of the algorithm is based on how well certain metric spaces embed in Banach spaces like this. And today I want to talk about one particular aspect of this. You can ask, okay, so if you have something that's too big, it doesn't embed into into R3. If you have something that's too complicated, like a random graph, it doesn't embed in Rn, it doesn't embed in Hilbert space. Say you have something that's not like that. Say you have something that's relatively small and highly ordered and sort of low dimensional in a sense. Can you embed it in Rn in a way that preserves its geometry, in a way that preserves the metric on that object? It turns out the answer is no. There are other properties that can prevent low-dimensional things from embedding in Hilbert space and other Banach spaces, and today I want to talk about one of those properties. I want to talk about one example of this, which is the Heisenberg group. So the Heisenberg group is a 3-dimensional nilpotent Lie group. It's a noncommutative group, and it's one of the simplest noncommutative groups. And basically what I want to do today is I want to show you that because the Heisenberg group is noncommutative, and the things that we're trying to embed it in, these Banach spaces and vector spaces, are commutative, it's hard to embed the Heisenberg group into a Banach space, into most Banach spaces. And so I want to tell you about 2 main points. One, that the non-commutativity of the Heisenberg group means that any embedding of the group into a Banach space has to be bumpy. It can't be smooth. It has to be rough. It has to have structure at many different scales. And I'll try to explain what I mean by that. And then 2, because of that, the Heisenberg group embeds better into Banach spaces that allow for bumpier embeddings. And so I want to get a little bit into the geometry of Banach spaces and how different Banach spaces are going to admit different sorts of embeddings. Okay. So let me start by introducing the Heisenberg group. The Heisenberg group is a 3-dimensional nilpotent Lie group. It's a group of 3x3 matrices like so, with ones along the diagonal, x, y, and z above the diagonal, where x, y, and z are real coefficients. This is a group. If you multiply 2 upper triangular matrices, you get an upper triangular matrix. And it contains a lattice. If you restrict these coordinates x, y, and z to be integers rather than real numbers, then you get a lattice. You get a discrete subgroup with 3 generators, x, y, and z, where x is the matrix with ones along the diagonal, a 1 here, and then zeros in the y and z coordinates. Y has ones along the diagonal, y coordinate 1, x and z coordinate 0. Likewise, z has z coordinate 1, x and y coordinate 0. And you can do some you can do some matrix multiplication. You can calculate that this is noncommutative. That if you take x and y and you take the commutator x, y, x inverse, y inverse, then that product is z. But x commutes with z and y commutes with z. And so this is a discrete subgroup of this nilpotent Lie group. So that's the algebraic structure of the Heisenberg group. What does the geometry of this group look like? Well, the geometry is based on something called the Cayley graph of the group. The Cayley graph of a group is the graph that you get by taking the vertices are the elements of the group. So that's, in this case, that's integer points in R3. And then we connect two vertices by an edge if you can get from one element to the other by multiplying by a generator. And so you can do the matrix multiplication. You can calculate that if you multiply by x, it increases the x coordinate by 1. If you multiply by y, it increases the y coordinate by 1, but also changes the z coordinate, also increases the z coordinate by x. And if you multiply by z, it increases the z coordinate by 1 and leaves the x and y coordinates the same. And so you can see, for instance, you can see the relations that we mentioned on the previous slide. X and z commute, because if you start at any point and you go in the x direction and then the z direction and then back in the x direction, back in the z direction, you come back to where you started. Y and z commute. If you start at any point and go y, z, y inverse, z inverse, you're back to where you started. But x and y fail to commute. If you multiply by x, y, x inverse, y inverse, you go around a sort of spiral. And you end up one step above where you started. And that noncommutativity, those spirals, have a very strong effect on the geometry. So it's okay so far? Is there anything I should say more about so far? I guess there's a chat attached to this, so you can also drop questions in the chat. I'll leave the events chat open. So these spirals, this noncommutativity has a strong effect on the geometry. And there are a couple ways that this manifests. First, there's a sort of scaling, or first, there are a lot of these spirals. So here, this is the spiral corresponding to x, y, x inverse, y inverse. If we stretch that out, we can also do the matrix multiplication that x squared, y squared, x to the minus 2, y to the minus 2 is equal to z to the fourth. And x to the n, y to the n, x to the minus n, y to the minus n is equal to z to the n squared. And in fact, these spirals are all scalings of one another. If you start with the small spiral here, if you stretch x coordinate by a factor of 2, the y coordinate by a factor of 2, and the z coordinate by a factor of 4, you get this bigger spiral here. And in fact, if you take the whole graph here and you squash the x coordinate by a factor of 2, and you squash the y coordinate by a factor of 2, and you squash the z coordinate by a factor of 4, then you get this picture here with this finer lattice and this bigger spiral here. And more generally, there's an automorphism of this group that sends x to x to the n, sends y to the n, and sends z to the n squared. So you have a sort of scaling of this graph. The other way that these spirals affect the geometry is that they affect shortest paths. Because when n is large here, and we look at this n by n spiral, then this spiral takes n steps, 2n steps, 3n steps, 4n steps to move up by n squared steps in the z direction. So when n is large, the length of this path is on the order of n, but the distance from here to here, the length of this vertical path from here to here, is on the order of n squared. And so if you want to go a long distance vertically, the fastest way to do that is to go around one of these spirals, is to go around one of these curves here. And that has a big effect on the geometry because it affects the shape of geodesics in this graph. This graph extends out infinitely. If I take 2 points that are far apart on this graph, say I take a point over here and a point over here, and they ask, what's the shortest path from here to here? Well, one thing we can say about that path is that it can't contain too many vertical edges. Because if that path contains a segment which is a long vertical segment, then you could replace that segment by a spiral and get something shorter. And so what you can say about those shortest paths is that the shortest path between 2 points can only contain a bounded number of vertical edges, can only contain, I think the bound is something like 16 vertical edges, because if you have more than 16 vertical edges, then you can do that. You can take you can take a vertical segment of your path, replace it by a spiral, and shorten the path. And so the shortest path between 2 points contains at most 16 vertical edges. And so if you have 2 points that are, 1,000, 10,000 units apart, most of the path between those 2 points consists of red edges in the x direction and blue edges in the y direction. Is okay? Okay. So this is this gives us a metric on the graph. We really want to think about the Lie group. We really want to think about not just these lattice points, but this whole three-dimensional object. So how can we use this to get a metric on the group rather than just on the lattice? Well, one thing we can do is we can take a limit of scalings. Remember that if you stretch the x-coordinate by n, the y-coordinate by n, the z-coordinate by n squared, that's an automorphism of the group, and it takes a lattice like this and gives you a finer subdivision like this. And so we can repeat this scaling as n gets larger and larger. We can get a sequence of scalings with denser and denser lattices, and then we can take a limit to get the metric on the entire group. That limit ought to have those same properties we saw for the graph. It ought to have, because we constructed it as a limit of scalings, it ought to have a similar n by n by n squared scaling. And because we know about shortest paths in the graph, shortest paths in the limit ought to be the limits of shortest paths in the graph. Shortest paths in the graph can't have more than 16 vertical edges, but then when we rescale those 16 vertical edges, they're going to get smaller and smaller and smaller. And so in the limit, the shortest path between 2 points should just consist of red and blue edges. So we should have, in the limit, we should get a space where, in a certain sense, you can only move in the red direction and the blue direction, and if you want to move in the vertical direction, then you have to go around. Then you have to go around in a spiral. And a space like that is something called a sub-Riemannian manifold. So, a Riemannian manifold is a manifold where you have a distance function defined by the distance between 2 points is the length of the shortest path between them. A sub-Riemannian manifold is similar, with the difference that in a Riemannian metric, every vector has a length. In a sub-Riemannian metric, every vector has a length, but some of those lengths are infinite. At every point, you have a subspace consisting of what are called horizontal vectors, and these are the vectors that have finite lengths. In the case of the Heisenberg group, the horizontal vectors are these planes in this picture here. You can see that these are the planes that are spanned by the red edges and the blue edges. These always contain the red edges and the blue edges. And we define the distance between 2 points to be the length of the shortest path between them. But because of because some vectors have infinite lengths, in order for that length to be finite, the path has to be horizontal. The path has to be tangent to these horizontal planes at every point. And so we're looking for paths that are tangent to these planes that only move in the red and blue directions. Now, because of the noncommutativity, because of these spiral paths, there still are horizontal paths from any point to any other point. Because if I want to move in the x direction, I can move along a red path. If I want to move in the y direction, I can move along a blue path. If I want to move in the z direction, then I can move in a spiral. I can go x, y, x inverse, y inverse, and move vertically. So I can still get from any point to any other point by a horizontal curve. So I can define the distance between the 2 points as the length of the shortest horizontal curve between them. It's just that that horizontal curve might go around in a spiral. Is this okay so far? Okay. And so, like I said, this ought to have a this ought to have this ought to have a scaling because it comes as a limit of scalings, and you can show that it does. You can show that for any t, if you scale the x coordinate by a factor of t, the y coordinate by a factor of t, the z coordinate by a factor of t squared, then you can show that that sends this distribution of horizontal planes to itself. So it sends horizontal curves to horizontal curves, and it stretches the length of every curve by a factor of t. So it scales the metric by a factor of t. And that tells us a lot about the shape of this object, because for one thing, well, it tells us about the shape of balls of radius epsilon. Because if I take a unit ball, if I take the ball of radius 1 around the origin, then I can rescale that by a factor of epsilon, multiply x by epsilon, y by epsilon, z by epsilon squared to get a ball of radius epsilon. But if I do that, well, my ball of radius 1 is roughly 1 by 1 by 1. If I rescale by epsilon, I should get something that's roughly epsilon by epsilon by epsilon squared. And so metric balls in this metric are, wider in the when epsilon is small, they're wider in the x and y directions than they are in the z direction, and as a consequence, that affects the Hausdorff dimension of this space. It means that every vertical line has Hausdorff dimension 2, because if I take a unit vertical line like this and I want to cover it by balls of radius epsilon, well, those balls are roughly epsilon by epsilon by epsilon squared. To cover that unit segment is going to take epsilon to the minus 2 of those balls. And so that means that that segment has Hausdorff dimension 2, and all these vertical segments have Hausdorff dimension 2. Is this okay so far? Are there any questions about this so far? Like I said, I have the events chat channel open, so feel free to drop questions in chat. So this is the geometry of the Heisenberg group. It's this three-dimensional space where you have these spirals that move you vertically. And so one question you can ask is, okay, can we embed this in a Euclidean space? Can we draw a picture of this can we draw a picture of this group in Euclidean space in such a way that it preserves the metric? And it turns out the answer is no. I guess I should say, and because this picture, one thing we can say about this picture is that it doesn't preserve the metric. We said that every vertical line in the Heisenberg group has Hausdorff dimension 2, but in this picture we've drawn all those vertical lines with dimension 1. So this is not a very geometrically accurate picture of the Heisenberg group. And we can ask, can we draw a better picture? Can we embed the Heisenberg group in Euclidean space in a way that preserves the metric? And it turns out the answer is no. This is the theorem of Ponceau and Semmes, that there is no bi-Lipschitz embedding from the Heisenberg group to Rn for any n. Remember that an L-Lipschitz map is a map from, in this case, from the Heisenberg group to Rn, so that distances don't stretch by more than a factor of L. So that the distance between f of x and f of y is at most L times the distance between x and y. And an L bi-Lipschitz map is a map that doesn't stretch distances too much in either direction. So the distance between f of x and f of y is bounded above by L times the distance between x and y. The map doesn't stretch distances too far. And the distance between f of x and f of y is greater than or equal to L inverse times the distance between x and y. The map doesn't squash distances by too much either. So Ponceau and Semmes showed that there's no bi-Lipschitz embedding from the Heisenberg group to Rn. There's no map that that preserves distances up to a constant factor L. And this theorem is based on a result of Ponceau, that every Lipschitz map from the Heisenberg group to Rn is what's called Ponceau differentiable almost everywhere. And so what it means to be Ponceau differentiable. Normally, when we talk about a map being differentiable, if I have a map from a line, from a map from R to R2, right? What does it mean that that map is differentiable? What it means is that if we take any point and we zoom in around that point, if we zoom in around that point, then that map is getting closer and closer to a linear map. If I zoom in at that point, that map is getting closer and closer to a linear map, and in the limit, it's going to converge to a linear map as we zoom in further and further. That notion doesn't quite make sense in the Heisenberg group because, well, what does it mean to be what does it mean to have a linear map from the Heisenberg group to Rn? Instead, you need a notion called Ponceau differentiability. And the map is Ponceau differentiable if, when you zoom in like this, the map converges to a homomorphism from the Heisenberg group to Rn, a map that preserves the group structure. And because the Heisenberg group is commutative and Rn is, or sorry, because the Heisenberg group is non-commutative and Rn is commutative, maps that preserve the group structure can't be injective. There aren't that many maps that preserve the group structure because the Heisenberg group is non-commutative and Rn is commutative. Any homomorphism from the Heisenberg group to Rn has to send the center of the Heisenberg group has to send the commutator subgroup of the Heisenberg group to 0. But the commutator of the subgroup of the Heisenberg group is that entire vertical subgroup, is all those vertical lines. And so any homomorphism has to collapse all the vertical lines in the Heisenberg group. And therefore, if you have a Lipschitz map from the Heisenberg group to Rn, it has to be locally approximable by homomorphisms. It has to be locally approximable by maps that collapse the vertical direction. And so the map has to collapse the vertical direction. It squashes the distances between vertically separated points. It fails to be a bi-Lipschitz map. Is this okay so far? Okay. So we can't embed the Heisenberg group into Rn by a bi-Lipschitz map. The noncommutativity of the Heisenberg group makes it impossible. What can we do instead? Well, one question we can ask is, instead of trying to embed the entire Heisenberg group, what if we just wanted to embed a piece of the Heisenberg group? So let's define, let's let B sub r be the ball of radius r in the lattice. So that's roughly the lattice points with coordinates between x coordinate between minus r and r, y coordinate between minus r and r, z coordinate between minus r squared and r squared. This is a ball with about r to the fourth many points. That's finite. And you can certainly draw a picture of a finite group. You can certainly draw a picture of a finite graph. You can certainly embed a finite graph into Rn without causing any self-intersections. And so you can ask, okay, how well can you embed that finite that finite space? It turns out that you can get a quantitative estimate of exactly how difficult it is to embed that finite graph, that graph with r to the fourth many points. And this comes partly from a theorem of Assaf, who showed that there is a map f from that ball radius r to L2, so that for any 2 points x and y in the ball, the distance between f of x and f of y is at most the distance between x and y. So this map doesn't increase any distances between points, and at least 1 over root log r times the distance between x and y. So it doesn't decrease the distance between 2 points it doesn't decrease the distance between x and y by more than a factor of square root log r. So it doesn't increase distances. It can decrease distances, but by no more than a factor of root log r. And so one term for this is that this is a map with distortion on the order of root log r. It distorts distances by a factor on the order of root log r. So how do we construct such a map? How do we construct a nice embedding of the Heisenberg group into Rn? Well, one way to do this is to look a little more closely at this theorem of Ponceau. So Ponceau said that every Lipschitz map from the Heisenberg group to Rn is close to a homomorphism almost everywhere. Why is that? Why does that happen, and how can we avoid that? Well, remember our picture of the Heisenberg group. The Heisenberg group is made up of these. The Heisenberg group is made up of these red lines going in one direction, and these blue lines going in the other direction. And so, if we take a Lipschitz map from the Heisenberg group to Rn, then the restriction of that map to any of these red lines is going to be some curve, some Lipschitz curve in Rn. There's a theorem called Rademacher's theorem that any Lipschitz curve in Rn is differentiable almost everywhere. And so that means that if we take almost any point and we zoom in around that point, and we zoom in around that point, we should get something that's closer and closer to a straight line. It should be differentiable. If we're careful, if we apply a little bit of measure theory, because we don't just have one of these red curves here, we have infinitely many of these red curves, one for each of the curves in this foliation. If we're a little careful, if we apply a little bit of measure theory, then what we can do is we can do a little better than that. We can find actually a ball in the Heisenberg group, so that we have these red curves going through the ball in the Heisenberg group, and those map to Rn in such a way that all of those red curves in the ball map to nearly straight lines in Rn that are all going in nearly the same direction. And if we're a little bit more careful than that, if we apply the measure theory argument again, then we can do the same thing for the blue lines. This ball has blue lines going through it as well. And we can ensure that we can find a ball so that those blue lines also map to nearly straight line segments in nearly the same direction. But then we have a problem. If we find this ball where the red lines all have about the same derivative and the blue lines all have about the same derivative, then we have a problem. Because on the Heisenberg group side, we're supposed to have, on the Heisenberg group side, we have these spirals. We have paths that go in the x direction, the y direction, back in the x direction, back in the y direction, and end up one step above where they started. But then the image of those under this map are going to be paths that go in the red direction, in the blue direction, back in the red direction, back in the blue direction. But the red directions are all almost parallel, the blue directions are all almost parallel, and so that path ends essentially where it started. And so that means that those 2 points, here and here, map to nearly the same point in Rn. And so what this is, and this is essentially why there's this failure to embed. Because of differentiability results, we can find pieces of the Heisenberg group that map to Rn by nearly straight lines like this, and then the noncommutativity of the Heisenberg group doesn't show up in Rn, and so points that are vertically separated in the Heisenberg group map to the same point in Rn. Is this okay so far? So if we want to see this construction of a SWOT, if we want to construct this map with low distortion, we need to avoid this. We need to make sure that our map doesn't have a ball like this. We need to make sure that our map isn't too smooth, because if our map is very smooth, then we can find pieces of our map that look like straight lines, and then we can glue those pieces together to find balls that map like straight lines, and those balls are going to collapse under our map. We have to avoid smooth curves in our map. And so we can ask, okay, what's the bumpiest possible curve? What's the least smooth curve that you can draw? The least smooth curve you can draw turns out to look something like this. So this is the idea of this is to construct something very similar to the Weierstrass function. Remember, the Weierstrass constructed a function which is continuous everywhere but not differentiable anywhere. Basically, by adding up oscillations at many different scales, we want to do essentially the same thing here. So what we do is we take a map from we consider a map from R to R to the K, where the coordinates are different sine waves of different amplitudes and frequencies, all the way from amplitude 1, frequency 1 to amplitude 2 to the K, wavelength 2 to the K. And then we look at the map that has those as its coordinates, and that map is going to oscillate at every scale. It's going to oscillate at scale 1 in this coordinate. It's going to oscillate at scale 2 to the K in this coordinate. So, you have some coordinates where it oscillates very fast, but very small oscillations. You have some coordinates where it oscillates very slowly, but with very big oscillations. Each of those coordinates is one Lipschitz. The derivative of each of these coordinates is bounded by 1. So if we just look at this point here, this defines a map with Lipschitz constant on the order of root k by the Pythagorean theorem. And if we want to get a 1 Lipschitz map, a distance decreasing map, we just need to rescale by a factor of root k. And if we do that, we get a map that looks roughly like this, which is what we'll say. We'll call this 1 over root k bumpy at k different scales, because basically at each individual scale, if I look at a ball of radius r, it is about 1 over root k r away from a straight line at that scale. And so I called this the bumpiest line. Why is this the bumpiest possible line you can draw? Well, one answer is basically because of the Pythagorean theorem. The Pythagorean theorem tells you that if you have a straight line of length, say L, and you want to add a bump, you want to make it epsilon away from a straight line, so you want to perturb it by epsilon L. Then, well, if you perturb, you get a broken line segment like this, and you can calculate that the length of this broken line segment is on the order of 1 plus epsilon squared times L. Perturbing it by epsilon L increased the length by a factor of epsilon squared. In particular, if you want to construct, the curve we constructed here is perturbed by a factor of 1 over root k at k different scales. And so the total increase in the length that you get by perturbing it at each of these different scales, every time you perturb it, the length increases by a factor of about 1 over k squared, 1 over root k squared, which is 1 over k. And so if you do that k different times, it increases the length by a factor of about, say, 2. And that's kind of the best you can do, because if you try to make it bumpier, or if you tried to increase the number of scales for the perturbation, the length would start to explode. So this is basically the bumpiest curve that you can get for a given length. It's okay so far? Okay. So then we can ask, okay, so this is the bumpiest line you can draw. If you want to embed the Heisenberg group, then you kind of have to set up a map so that every one of those red and blue lines in the Heisenberg group maps to a curve like this, maps to one of these very bumpy curves. And we construct that again with this same sort of Weierstrass idea. We want to combine oscillations at many different scales. So we can define a map, call it sigma I. This is kind of like one of the sine waves we used on the previous construction. Sigma I is going to be 1 Lipschitz, and it's going to have amplitude about 2 to the I, and it's going to have wavelength about 2 to the I. The only difference is that it's defined on the Heisenberg group rather than on the real line, but that's not too much of a problem. And then you can define a embedding of the Heisenberg group by defining f of x is 1 over root k times root kx, sigma kx, sigma k minus 1x, all the way down to sigma naught x. So you've got k coordinates. Each of those coordinates is 1 Lipschitz. So by the Pythagorean theorem, this whole thing is root k Lipschitz. We rescale by a factor of 1 over root k to make it 1 Lipschitz. And then we claim that this embeds the ball of radius r into L2, into Hilbert space, with distortion on the order of root log r. And the reason for this is because if you take 2 points in BR, remember BR is the ball of radius r in the lattice. So if you have 2 points in BR, the closest they can be is if they are adjacent in the Cayley graph. The closest they can be is distance about 1. The farthest they can be is distance about r, the radius of the ball. And so if we look at the images of those 2 points, f of x and f of y, well, the distance between those 2 points is between 1 and r. So it's on the order of 2 to the I for some I between 1 and log r. And so there's going to be one of these coordinates that corresponds to that distance. There's going to be one of these oscillators that oscillates at about that wavelength. And so that x and y, you can find one coordinate where x is at the top of your wave and y is at the bottom of your wave. You can find one coordinate where the distance between f of x and f of y is on the order of the distance between x and y. The only issue is that because of this rescaling factor here, you have to divide by root k. You have to divide by root log r. And so that's where your distortion comes from. You can have a map which is bumpy at each of these different scales, but the price you pay for that is that it increases the Lipschitz constant. And so in order to make your map 1 Lipschitz, you have to rescale. And when you rescale, that causes some distortion. Okay? And this is optimal. So it's a theorem of Austin, Naor, and Tessera that this is optimal, that this is this is roughly the best you can do. That any embedding of BR into L2 has on the order of root log r distortion. And the reason for that is, well, one reason for that is essentially what we talked about curves earlier. The one reason for that is essentially the Pythagorean theorem, that in order to make a map that is epsilon bumpy at one particular scale, it's going to cost you something on the order of epsilon squared. And so if you want to if you want to construct a map with root log r distortion, you're forced to make it 1 over root log r bumpy at as many scales as you can. But because of the Pythagorean theorem, the number of scales where you can do that is going to be on the order of log r. And so if you have a ball of radius r, that the metric has scales between 1 and r, you need log r many different scales in order to cover all of those scales. And so you can only have root log r bumpiness at each scale, which forces you to have at best root log r distortion. Is it okay so far? Okay. So then So this tells you, this gives you a pretty complete characterization of one Banach space of L2, the Hilbert space. What are other Banach spaces? Because in L2 we saw that it had to do a lot with the Pythagorean theorem. If you take other Banach spaces, you don't have the Pythagorean theorem anymore. If you take LP, you have a version of the Pythagorean theorem with exponents on the order with exponent p rather than exponent 2. And so we should expect that the embeddings in LP should depend on P. And you can do that. First, when P is bigger than 2, then you can modify this construction to construct better embeddings into LP than in L2. You take these same oscillators, sigma k, You do this same construction where you construct a map which uses one of these oscillators in each coordinate, and in order to make that one map one Lipschitz, you need to rescale. But because you're in LP and not in L2, you rescale by pth root of log r rather than root log r. And you can check that this embeds B sub r into LP with distortion like the pth root of log r. And there's a theorem of Laforgue-Naor that any embedding of B sub r into LP has at least this much distortion. Again, more or less because of the Pythagorean theorem, because this is the right version of the Pythagorean theorem for LP. And so let's draw this in a graph. So we can define what's called the distortion exponent of B sub r in all these different spaces. It embeds in L2 with distortion on the order of root log r. It embeds in LP with distortion on the order of the pth root of the pth root of log r. And so these results tell us that as p increases, the distortion gets smaller and smaller. If we increase p, we get Banach spaces that allow for bumpier maps, and so the distortion goes down. In the limit, when p goes to infinity, any metric space embeds isometrically in L infinity, and so we should expect to have no distortion at all. Conversely, okay, well, that leaves a gap between p equals 1 and p equals 2. What happens in that gap? What happens when we decrease p? Well, when we decrease p, it turns out to plateau. You can show that. Naively, you might expect the distortion to go up, and in fact, if you do exactly the same construction that we did for p greater than 2, you would have to the distortion would go up. But there are different constructions with lower distortion. There's a theorem of Dvoretsky that any infinite dimensional Banach space almost contains a copy of Rn. Almost contains a copy of Euclidean space of arbitrarily large dimension. And so what you can do is you can take that large copy of Euclidean space, you can take that copy of Hilbert space inside your Banach space, you can construct an embedding into that copy of Hilbert space, and that embedding has exactly the same distortion as the embedding into L2. And so when p is between 1 and 2, you have this plateau. And then you leave one, which leaves one more exponent to look at, which is p equals 1. It turns out that remarkably, there's a discontinuity when p equals 1. That at p equals 1, you have you have root log r distortion again. Fourth root log r distortion again. That in some way, the Heisenberg group embeds better in L1 than it does in any of these other LP spaces up to L4. And so that's what I want to spend. That's what I want to talk about for the last, I guess, couple minutes. Is why there's this distinction between L1 and why there's this discontinuity at L1. So before I do that, are there any questions about anything so far?
Please pause me if it's a long one, but you've shown like a loop becoming closed when or like they're forming a closed loop when embedding Heisenberg group into Rn. A few slides back, it made me wonder if there is any role that like cohomology classes play in detecting like bumpiness of embeddings at different scales, like particularly like the RAM cohomology of the image of the Heisenberg group under like these one Lipschitz embeddings with oscillatory behavior.
Yeah, so there's a theorem of there's a theorem of Yehuda Shalom and a theorem of Roman Sauer that deal with with how cohomology changes under what are called quasi-isometries. But a special case of a quasi-isometry is a bi-Lipschitz map. And so what you can do is those maps, if you have a map from if you map from, in this case, we have been talking about the Heisenberg group to Rn, but in general, you can talk about a map from one nilpotent group to another nilpotent group. You can look at de Rham cohomology. De Rham cohomology of a nilpotent group is generated by left invariant differential forms. The problem is that when you pull back a left invariant differential form, the pullback you get is no longer left invariant, and so you have to do some sort of averaging construction to get back to a left invariant form again. So yeah, so you can and so what Shalom and Zauer prove is that if you have a quasi-isometry between two nilpotent groups, if you have a map that preserves the metric enough, then that induces an isomorphism of cohomology algebras. That in some sense they have the same cohomology, and you can construct some pullback. So even though that map isn't a homomorphism, you can still construct some pullback of differential forms.
Oh, thank you so much.
Sure. Oops. Oh shoot. Did I lose my stream? Okay. No, you can still see that. Okay. Okay. How much time do I have?
22 minutes.
Oh, we're going to 4:30? Okay. Okay, so I'll try to end before then, but that's good to know. Okay, so we were just saying that you have this picture where the Heisenberg group is hardest to embed in L2. As you increase P, it gets easier to embed. As you decrease P, there's this discontinuity where it suddenly gets easier to embed when P equals 1. And so this turns out this is a weird phenomenon. One consequence of this is that you can use this to construct a metric space that embeds bi-Lipschitsly in L1 and L4, but not in any of the LP spaces in between. And this is the first construction of a metric space like that. Basically, what you can do is you can take the Heisenberg group, you can modify it by just enough. You can modify the metric by a factor of 4th root log r. That's enough so that it embeds in L1 and embeds in L4, but it's not enough for it to embed in any LP space in between. And that gives you a metric space that embeds in L1 and L4, but not anything in between. And so, yeah, so today what I want to do is I want to try to explain why this discontinuity happens, why the Heisenberg group is easier to embed in L1 than in L2. So one of the main reasons that this happens is that all the techniques that we just talked about based on differentiability, all those don't work anymore in L1. If you have a Lipschitz map to L1, if you have a Lipschitz map to Rn or Hilbert space, there's Rademacher's theorem, which tells you it's differentiable almost everywhere, but Lipschitz maps to L1 don't have to be differentiable anywhere. There's a classic example, which is you have the map from the unit interval to the space of L1 functions on the unit interval, which sends T to the characteristic function of the interval from 0 to T. So you send, so this is a step function like so. You can check that this is an isometric embedding. That if you take if you take Fs and Ft, well, Fs and Ft are two different characteristic functions like this. The distance between them is the area of this rectangle is absolute value of S minus T. So the distance between f of s and f of t is the distance between s and t. And so this is an isometric embedding, but it can't be approximated by a linear map anywhere. It's not differentiable anywhere. And so this, because of this, the techniques that we used based on differentiability before no longer work. We can no longer get bounds on the distortion using differentiability. And that opens up a whole new class of possibilities, because now we can consider maps that are like this. We can consider maps from the Heisenberg group to the set of L1 functions from the Heisenberg group, so that the image consists of 0, 1 functions, so that f of x is the characteristic function of some set S sub x. So the easiest way to do this is to construct this equivariantly. We pick a set S in the Heisenberg group, let mu be the Haar measure, and let f sub s be the function from the Heisenberg group to L1 function of the Heisenberg group that sends G to the characteristic function of a translate of S. I've got this S inverse here. The reason I have that inverse here is because I want this formula that you can calculate that f sub s induces the left invariant metric, so that the distance between fs of p and fs of q is the measure of the set of G in H, such that this intersection has one element. What that means is that this is the set of translates of P and Q, so that one of those points lands inside S and the other one doesn't. This is a little bit this is a little bit complicated. So let's look at an example. So for example, if you take D to be the unit ball in H, so here's our unit ball D, and we take 2 points, let's say P and Q. Let's draw these a little further apart. If I take 2 points P and Q that are far apart, where the distance between them is large, then I can ask, what is the distance between f of p and f of q? Well, this formula tells me that that distance is the size of the set of G. This is the number of elements of the Heisenberg group. So if I translate this segment by G, then one endpoint lands inside the set and one endpoint lands outside the set. So it's going to count all of these elements. It's going to count all of these elements where Q lands inside the set, but P doesn't. But it's going to ignore all of these elements where P and Q are both outside the set. We're just counting the elements where this segment crosses the boundary. How many of those elements are there? Well, if P and Q are very far apart, then all those elements are going to have either P inside the set or Q inside the set, but you can't fit both of them inside the set. And so the number of elements like that is basically twice the measure of D, twice the measure of this ball. The distance between f of p and f of q is on the order of 1. What happens if we take a different pair of points? We take the same set, the same unit ball, but we take 2 points that are, say, much closer together. So t is less than 1, and we take p and q that are about t apart, like so. Then we can do the same thing. We want to count the number of translates of this set where one of the endpoints lands inside D and one of them lands outside. So what are those points? They're going to be all these like this, where one endpoint is inside and the other one is outside. There are going to be all these like this, where one endpoint is on the inside, one endpoint is outside. But we're not going to count things like this. We're not going to count things like this. We're just going to count the ones along the boundary. How big is that set? Well, the size of that set is basically going to be, this side of the ball and this side of the ball, where the thickness of that region is on the order of t. So the measure of the points that have this property, the measure of the translates that take one end inside the ball, one end outside the ball, is going to be on the order of the length of the segment. Is going to be on the order of the distance between P and Q. So if P and Q are horizontally separated by a short distance, then this map sends them to about the right distance apart. This map preserves the distance between those 2 points pretty well. The problem with this map is vertical lines. The problem is always these vertical lines, because if we take the same set and now we take 2 points P and Q that are vertically separated, then again we're looking for translates that come that send one of these points inside the set, one of the points outside the set. So that's going to be a region around the top boundary, a region around the bottom boundary, where the thickness of that region is on the order of t. So the distance between f of p and f of q is going to be on the order of norm of t. But the problem is that because we're in the Heisenberg group, the distance between P and Q the length of this z to the t is on the order of square root of t. And when t is small, t is going to be much smaller than square root of t, and so this map is going to collapse vertical segments again. The problem is always that our maps collapse vertical segments. So how do we fix this? How do we construct a map into L1 with low distortion? Well, we need to modify our set. We had this set D, which was a ball, and we saw that it preserved horizontal lines pretty well, but it collapsed vertical lines, basically because the number of times that it crosses these horizontal line segments is relatively large, but the number of times it crosses these vertical line segments is too small. How do we fix this? Well, we want to modify our surface. We want to modify our set so that it cuts as many vertical lines and as few horizontal lines as possible. One way to do that is instead of making it smooth like this, to make it more wavy. Because if you have a set which oscillates more like that, then it's still going to then those oscillations mean that it crosses more vertical line segments. And so we can construct surfaces in the Heisenberg group that cross a lot of vertical line segments, but not too many horizontal segments, basically by taking a vertical plane and then making it bumpy. The problem is that you can see from the picture that if you do this, if you start with this vertical plane and then you try to make it bumpy, if you try to add, bumps to this, I guess sorry, that's a little bit hard to see, but I hope you can tell what I mean. If you start adding bumps to this to make it cross more vertical lines, to cut more vertical lines, then that's also going to cut more horizontal lines, because these horizontal lines are going to cross through those bumps. And so there's going to be a trade-off here. We can make our surface more complicated, we can make it cut more vertical lines, but in order to do that, it's also going to cut more horizontal lines. But if we make that trade-off, we can construct very bumpy surfaces in the Heisenberg group, basically like so. You start with a vertical plane, you add a bump to the middle of that. If you do that, well, the slope of the horizontal lines is going to change on that bump. And so you see that here, your horizontal lines start to tilt as your x coordinate increases, like so. In the middle of the bump, they're sloped more than at the sides. And so then you add another collection of bumps on top of that. And you do your best to make sure that these new bumps line up with those horizontal lines. Those new bumps are as horizontal as possible. That means that your new bumps are tilted a little bit in the middle of the surface, and they're tilted less on the sides. And you repeat. You go at smaller and smaller scales. You keep on adding more and more bumps, doing your best to line them up with the horizontal curves on the surface. And in the end, what you get is a surface like this. You get a very bumpy surface with the property that if you go from the top of the surface to the bottom, you will cross in and out of those bumps many, many, many times. It crosses vertical lines very frequently, but if you take a horizontal line in the Heisenberg group, then that line is going to go along. It's going to go the long way along these bumps. It's going to cross many fewer times. And so this gives you a way of constructing a surface which is very bumpy. It crosses vertical lines as often as possible and horizontal lines as rarely as possible. Every time you do this, there's a cost. Adding a layer of bumps of depth epsilon adds epsilon to the fourth to the perimeter. And so if you want to construct log r many layers of bumps, enough to embed the ball of radius r, the depth has to be on the order of log r to the -1/4, or the size of the surface will explode. And so you can use this to get the desired embedding with distortion on the order of fourth root log r. And so this is this is one of the reasons why there's this difference in the distortion between L1 and L2. In L2, well, I guess, yeah, so up to a constant, this is the bumpiest possible surface. Surfaces like this lead to the best possible embeddings. And Assaf and I proved that this is in fact optimal, that the L1 distortion of BR is in fact, like I showed on that graph, is on the order of 4th root log R. The basic reason behind a lot of this, the upshot of this whole talk, is that maps from the Heisenberg group to Hilbert space to L2 are governed by differentiability, or governed by how bumpy curves in L2 can be, and they're governed by the Pythagorean theorem. Maps from the Heisenberg group to L1, on the other hand, because of this construction with characteristic functions, because of this equivariant construction, maps from the Heisenberg group to L1 are governed by how bumpy a surface we can construct. And so we can so it turns out that we can construct much bumpier surfaces in the Heisenberg group than we can construct lines in Rn. And so you get a difference in the distortion between between L1 and L2. And so this is so ultimately, you know, what this tells us is that this noncommutativity in the Heisenberg group has geometric implications. It's hard to embed the Heisenberg group into Banach spaces because the Heisenberg group is noncommutative and Banach spaces are vector spaces, are commutative. And so you can ask, what other properties like simple metric spaces are hard to embed in Banach space or hard to embed in Rn. So that's essentially what I wanted to talk about today. I just have one more picture to show, which is I didn't have a place to fit this in the talk, but this is one of my favorite surfaces in the Heisenberg group. This is something called an intrinsic Lipschitz graph, which has this same philosophy of this is a surface which is where you're trying to make it as bumpy as possible. And the way you do that is by adding bumps in the direction of horizontal curves. You're adding bumps where the slope of those bumps depends on the x-coordinate of the surface. And because you're in the Heisenberg group, you can have a surface which is much bumpier, much more jagged, much rougher than surfaces in Euclidean space. So, okay. That's everything. So, thank you.
Yeah, I have a question regarding so yeah, you've talked about different kind of surfaces. Like, is there something you can say about like, you know, what like do the tools from one surface, is it easy to study like another class of surfaces? Or is it like, you know, they're very different from one another and it's very difficult to import, you know, certain tools from certain kind of surfaces, you know, that you're studying here versus, you know, a different class?
So the tools that go into this are a field called geometric measure theory. So geometric measure theory originated from studying minimal surfaces. You have, you know, soap bubble problems. You have a surface with some given boundary. What's the smallest area that surface can have? And so one aspect of geometric measure theory, one subfield of geometric measure theory, is something called uniform rectifiability and quantitative rectifiability, which is exactly these questions of how bumpy a curve, how bumpy a surface can you construct. And so you know, so we talked a little bit about, yeah, right, how the Pythagorean theorem gives you a bound on how bumpy a curve in Euclidean space can be. It turns out it's much more difficult because surfaces are harder to parameterize than curves are. It turns out that you can say very similar things about surfaces in Euclidean space using tools, like I said, called uniform rectifiability. That in some sense, if you have a surface in Euclidean space with bounded area, it can't be too bumpy at too many different scales, because if you take a smooth surface and you add bumps to it, it increases the area. And you can quantify exactly how much. And so one of the things we're doing here is basically extending these tools from geometric measure theory to nilpotent groups and the Heisenberg group, and trying to understand how they're the same and how they're different. And one of the differences is this 1/4 exponent versus this 1/2 exponent. That the Pythagorean theorem in Euclidean space gives you this 1/2 exponent, but surfaces in the Heisenberg group, you don't have the Pythagorean theorem anymore, and so you get a different exponent. You get this 1/4 exponent rather than a 1/2 exponent. You get bumpier surfaces in the Heisenberg group than you do in Euclidean space.
Okay, I see.
So I wanted to ask about, like, you mentioned that geometric measure theory comes from minimal surfaces, and I just wanted to ask, like, in context of this, and how does like use of Haar measure influence like the regularity in minimal surfaces, and especially like if there is any role of these um, like the connection to the bumpiness of embeddings being at like different scales.
It's hard to say. So minimal surfaces in the Heisenberg group, and in sub-Riemannian manifolds like this are much less well understood than they are in Euclidean space. So it's something I'm interested in. It's something I've tried to work on, but there's still a lot of open questions about how minimal surfaces in the Heisenberg group should behave. Like even the most basic the open question. So what the one of the fundamental results of geometric measure theory is the theorem that if you want a subset of Euclidean space that bounds the most volume for the least perimeter, it's the round sphere, right? The round soap bubble is the most efficient soap bubble. But in the Heisenberg group, this isn't known. There's a conjecture as to what the minimal surface should be, what the ideal surface should be, but we aren't able to prove it.
Thank you. Uh, on the server, we explore singular learning theory, and in there we started thinking a lot about like resolution of singularities. So I just wanted to ask a question about this. Is there any connection between any? It's kind of a general question. Is there any connection between like measure theory and singularity resolution?
Geometric measure theory and geometric analysis more generally is very interested in singularities because there are a lot of questions that are like there are a lot of questions revolving around partial differential equations and a lot of geometric phenomena that are described by partial differential equations. And so you do a lot of there's a lot of work done on what sort of singularities can occur in the solution of a PDE, and how can you continue the flow, or how can you continue the solution past that singularity? I don't know whether it's related. I don't know the relation to algebraic geometry. I don't know very much algebraic geometry, but the study of singularities shows up in lots of different areas.
Thank you so much. Thank you. This was a really interesting talk. Thank you so much.
Thank you. More questions? Well, thank you very much for inviting me, and thanks for coming to the talk.